Sound check, sound check. Well, today we're going to be introducing Chapter 7, and Chapter 7 starts out with the concept of identities. Today we'll be looking at basic trig identities. And identities are something new for us. We haven't gotten a chance to explore those. So one of the things I hope for us to do in today's lesson is to understand what identities are, why we need to understand and make use of identities, and how that is going to look. So we'll get a chance to kind of do an overview here. But a lot of the background that we have already been working with here is critical to being able to make good use of identities. So for example, knowing your trig values for all of the special angles in both degrees and radians, as well as understanding the graphs. These are things that will come in handy as we go through and do more of these lessons, and you'll see how they apply here. So first of all, let's figure out what an identity is, or let's describe what an identity is. An identity is simply a relationship that is true for every value of the variables. So this is the what. This is the what of what identities are. They're simply relationships or simply equations which are always true. Now we don't see a lot of identities in any of our prior math. There are some things that we are perhaps familiar with that would be like identities. Identities don't really show up in earlier levels of math in a clear way, simply because they're not needed. They're not needed. If we're just working with the variable x and we're not looking at complicated relationships between a wide variety of functions, maybe the few identities that we know of, we can look at an example here of an identity that you should already be familiar with. Most identities in algebra are trivial. That is to say, they don't give us very much information. But we can think about an identity like this. The log base b of a is equal to the log base c of a divided by the log base c of b. This is true for all a, b, and c, for which we would be able to determine logarithms anyways, right? Obviously we can't have zeros or negative values in places here. We have to be very careful about those sorts of things, but for any well-behaved values of a, b, and c that would normally be related to logarithms, this is a true statement, and this is true for any values of a, b, and c. So we would call this an identity. The left-hand side and the right-hand side look fundamentally different, and they're still always equal to one another. Okay. So let's talk for a moment now about why identities are so important. Why do we need these objects in mathematics? Well, if you think about the progress that we have gone through with trigonometry, we have gone through several steps in trigonometry. We have looked at basic equations in trigonometry, basically the definitions. We have looked at graphs of trigonometric functions, and if we carry this through to the logical endpoint, we think about what we normally do when we understand or learn about functions, or when we learn about other kinds of operations, is the last step here will be to work with trigonometric equations. And that's one of the major things we'll be seeing in this chapter, are these trigonometric equations. We'll be working to understand how trigonometric equations are built, how to solve them, and it turns out that identities are a major portion of that connection there. That ability to solve these trig equations is a fundamental need for identities. You already know some identities, so we'll go ahead and list those out here. most of the identities you know are already fairly trivial. There's a class of identities that are known as the reciprocal identities. The reciprocal identities are just basically, if you will, almost the definitions, or they could be used as the definitions of some of the operations we already know. So for example, the cosecant of an angle is 1 over the sine of an angle. This relationship is true for any value of the variable theta that we choose to evaluate at. The left-hand side and the right-hand side are always equal, therefore this is an identity. Another reciprocal identity that we know is that the secant of an angle is always 1 over the cosine of that angle. Again, it's true for all values of the variables. And of course we have that the cotangent of any angle is always the reciprocal of the tangent of that angle. So these are the reciprocal identities. These can be useful sometimes when we're trying to simplify expressions that might contain things like cosecants, secants, or cotangents, and we want to rewrite it in terms of sines, cosines, and tangents. Admit it, we're much more comfortable with sines, cosines, and tangents. So if we can rewrite our equations using those, usually we'll be able to do a little bit more with those equations. Those aren't the only ones that you know. We can also look at a slightly different set of equations, but to do this I'm going to go back to looking at a right triangle and just observe something here for a moment. If we have our adjacent side, our opposite side, and our hypotenuse, we can begin to make some connections here. For example, if I look at the sine of any angle, the sine of this angle here will be simply the ratio of the opposite to the hypotenuse, and the cosine of any angle is the adjacent divided by the hypotenuse. It's this ratio. What we're doing here is we're going to derive an identity. We're going to show that there is an identity lurking in some connections here and something that is useful for us to look at. What I'd like to do is compare these two to the tangent ratio. The tangent of any angle is simply the opposite side divided by the adjacent. Now notice that opposite and adjacent appear in sine and theta, and in both cases they're divided by the hypotenuse. If I take the ratio of sine and cosine, then we will end up with an interesting and useful expression here. So let me take for a moment and just evaluate the sine of theta over the cosine of theta. This is the opposite over the hypotenuse divided by the adjacent over the hypotenuse. And you can see from several different ways that the hypotenuse portion of this expression is going to cancel, and we're simply left with the opposite over adjacent. However, we know from our work with right triangle trigonometry that in a right triangle the ratio of the opposite side to the adjacent side is the tangent. So we have another identity here, and this is one of the identities known as a quotient identity. Quotient here simply meaning we're taking a ratio or division, and the most important one of those is the tangent of theta is the sine of theta divided by the cosine of theta. And you may have used that before, you may have seen us use that in class before, but here we've actually shown it, and this is in fact an identity. It's true for any value of theta that you would choose to use. The left and the right hand sides will be the same. We can get one for cotangent. We can get a quotient identity for cotangent simply by making use of the reciprocal identity and seeing that since tangent and cotangent are reciprocals, the right hand sides must be as well here. So we can say that the cotangent of theta is always the cosine divided by the sine. And one of the powerful things that identities allow us to do is rewrite expressions in terms of different trig functions. Oftentimes there's a good need to do that. Well, we are talking about basic trigonometric identities today, but we're going to be looking at one of the most important ones today as well. If there's no identity that you remember except for one, the one that you should remember is the one we see here right now. We're going to look at what is called the Pythagorean identity. And this is an identity that we have not seen and we have not worked with before. And all of these identities come from approaching problems in different ways. What I'm going to look at here is I'm going to take a look, to begin with this morning, at the unit circle. So let's take a look at the unit circle. Recall that the unit circle means that our radius here is 1. And if we think about a point then on the unit circle, we make a right triangle here. Recall that this point has the x-coordinate that's equal to the cosine of theta and the y-coordinate that's equal to the sine of theta, where theta is the central angle here, like this. Well, we could draw this in a slightly different way. I can just take this triangle out of the unit circle, and here our triangle has a hypotenuse of 1. The vertical or opposite side has a length equal to the sine of theta. The horizontal or x side, the adjacent side, has a length of cosine theta. So here we have a triangle that shows these three sides, and we got this triangle from the unit circle. However, there's something that we can apply, there's a rule that we can apply to this triangle that we haven't thought about before, and that is the Pythagorean theorem. So if you think about our right triangle here, it must be true that the cosine of theta squared plus the sine of theta squared must equal 1 squared, or just 1. So this is the Pythagorean identity for sine and cosine. It's a very useful, very useful connection, a very useful way for us to solve problems. However, all these parentheses make things a little bit confusing, so I need to introduce you to a very important notation that we will be using in this chapter, and pretty much you'll be using for the rest of your trigonometric lives. Instead of writing parentheses cosine theta squared, what we're going to do is we're going to write cosine squared of theta plus sine squared of theta, and that will equal 1. So we write the squared after the cosine or the sine. The reason that we do that is because if we were to write an expression like the cosine of theta squared, this is ambiguous. This is not clear what we mean. Are we squaring the cosine? Are we squaring the theta? What's going on here? So this is not a good notation to use. Rather, we put the squared after the trig function, cosine or sine, and before the angle. So let's go ahead and list. There are several other Pythagorean identities. I'll go ahead and list those off, and then we'll talk about examples of how we might use them, since that was another question we had today. Our Pythagorean identities start with this most important one. The cosine squared plus the sine squared of any angle equals 1. If we start with this, we can derive or generate other Pythagorean identities. Suppose I take and divide every term here by the cosine squared. Okay. The first term here then will become a 1. The second term, sine squared over cosine squared, well, sine over cosine is tangent, so sine squared over cosine squared will be tangent squared theta. And 1 over cosine is secant, so 1 over cosine squared will be secant squared theta. Here is another of our identities. Okay. And of course we can take our original expression, the original Pythagorean identity we had for sine and cosine, and we can divide everything by sine squared of our angle and come up with a new identity here as well. Cosine divided by sine is cotangent, so we have cotangent squared theta plus 1 is equal to cosecant squared of theta. And this is our third Pythagorean identity. So these are all three very important identities, things that we would like to be familiar with over the course of the year. These are things we'll be using very much in the next chapter. So we want to be comfortable with those.